So either we have numbers or we have codes that represent other things. So I think in this lecture, I actually show y'all what we call the key scan code that's used by the compatible computers, the Windows compatible computers. That what we used to call them IBM compatible, but IBM don't make laptops anymore, or even they're back in the mainframe and supercomputer business altogether now. So everything has some way or the other has to be translated over to the binary ones and zeros, because some of it's not. Some of it doesn't deal with numbers. So when I look at the keyboard on my computer, you see a lot of things on there besides ones and zeros. So that means we have to pick up a bunch of codes. So if I wanted to send a message up to this display on the screen, then I've got to be capable of sending it the letter A, right, or the letter B, or the C, or D. And it's got to be in ones and zeros. So a code is when we use something to represent something else. If this is going to load, guys. Here we go. We had a review of the decimal number system. Then we looked at the base of a number system. So the three bases that we use in or the four bases that we use in programmable controllers is decimal, of course, which is the one we prefer. And then, of course, we have binary, which is what everything is inside a computer. Then we looked at octal, which is a way that we can represent large binary numbers with fewer digits. And this is for us. It's not for the computer. Computer has no idea what octal is. We tell the computer by putting a code out there that we're entered in an octal, and then the application knows how to convert it over to binary. The codes, so everything you see up here is a code. Everything you see on this screen is a code. That's actually stored in the computer. So the computer has no idea what the uppercase H is. It has nothing. It has no idea. Currently, we originally used a code called ASCII code, which is American Standard for Code for Information, which is still used by PLC because it's an 8-bit code. Unicode, so if I come over here and say insert symbol, these are the codes. So here's the letter H. Do I see the letter H? Well, here's the letter A. That's good enough. And this is the actual code down here. If y'all can see it, I can't make it any. That's actually stored in the. And this is not even in binary. This is a 16-bit code, which gives us 65,536 different character combinations. But they don't display it in binary, but the computer displays it in hex. So this is hexadecimal. So the actual code would be 000000001000001. That's actually code that's stored in memory and sent to the in the computer. So when you hit a key on a keyboard, when you enter this into this document right here, it's not an E. It's the code for an E that's actually stored into the word processing software.
Unicode is all the letters and the numbers.
And the characters. Originally, the first code that they used to represent letters and control characters was something called ASCII. And it's called the American Standard Code for Information Interchange. When we program websites, we program it, and it's not even a programming language, it's a formatting language. It's called HTML, it's called Hypertext Markup Language. And basically, it was nothing but ASCII. So you'd put the ASCII code for a space. You'd put the ASCII code for a carriage return. You'd put the ASCII codes for all these in the center. Luckily, it would translate over for you. But it's the American Standard Code for Information Interchange. So the only characters that were available to the world when we went to the internet was English. So if you programmed a website, it had to be in English, period. Well, they realized as the internet started going and going around the world, they said, well, you know, I might be in Japanese and I want my website to be in Japanese, or I might be in this country and I want my website to be in that. So this is where they came up with Unicode. So Unicode, and they don't install all of it. I don't know if you ever went to a website and a little gray box pops up and say you need to download the codes for this website. So they don't put all those codes inside your computer because that's a lot of space. You think about it, that's 16 bits. I mean, that's 16 bits and 65,536 characters, each one of them taking 2 bytes of memory. If you loaded that in with your word processor or your web browser, you'd eat up tons of memory inside your computer to be able to recognize those codes. But you can see this, so there's a Latin alphabet. It's got Greek by default. So it can actually do, right now with Unicode, they can actually do every known written language that's available today with 65,536 characters. So you can see. And so what's actually stored in the computer is not the letter E. It's a binary code for the letter E. Now my computer understands that, and all these are just a bunch of dots. That's all they are, a bunch of dots. And if we display text, then they can use codes. If we display graphics, then you're controlling each little pixel at a time. So what we're saying is that, and of course, so they're not displaying it in, actually Unicode's a lot bigger, but they're not displaying it down here in binary because that would be cumbersome for us too. So it actually displays it using a code for what? FBE4. And so normally when they do text like that, and by the way, everything's graphics now. So everything's graphics now. Used to, when we was on ASCII and everything was text, is we would have a ROM inside the computer, and the address would come in and be the ASCII code, and then the bit pattern would be what was stored inside the ROM for that address to be turned for what bits to run. But now everything is graphics, which means it eats up a bunch of memory, and that all depends on your resolution, and the number of colors that you do, how much memory your video card actually uses. So, and that's why, so hex, the computer has no idea what hexadecimal is. What hexadecimal is, it allows your computer or you to enter large binary numbers with very few digits. So like I called out that number a while ago, I came up here and I called out this number. Let me put let's do it simple again. So if I wanted to display this, by the way, I'll have to show you. You got a key sequence. This computer won't do it because I don't have a numeric keypad, where you can enter these codes directly, but you have to enter them in decimal. So if I come over here, I don't know. I don't think I know Windows does it. Let's see if this does it. Oh, I don't have a numeric keyboard on. So it can't be the code for the one across the top is different than the code for the one that's over on your numeric keypad. So if you want to enter Unicodes or ASCII codes directly, you have to have a numeric keypad. But you could actually hit Alt and enter the decimal equivalent on your numeric keyboard, and then the character would pop up, which is pretty cool. Or you could also enter using Unicode directly. But that pattern has got to be inside the computer, so you can't enter a Unicode that's not inside your computer already. Does that make sense? So they don't download all those characters. So we looked at bases, we looked at real numbers, or most of your computers. This RSLogic 500 calls it floating point numbers, by the way. And then we were getting into binary and then hexadecimal. So what we do in binary or hexadecimal is we could use a calculator, but that's going to be cheating, guys. You can't use it. And I'm a firm believer if you can't do it yourself, you don't need to depend on a calculator. So even if I was going to go to decimal, if I was going to go from decimal to binary, and I didn't have a calculator, then I would go through binary by using that subtraction method. Everybody okay on binary?
The test review says, you need to be familiar with addition and subtraction.
You're not gonna do it, but it's kind of familiar. So let me add, so I wish, of course, it's a lot more cumbersome because it takes more digits. But, I wish it was, in binary because you don't have to worry about what 9 plus 9 is, because you're gonna add 1 plus 0. 0 plus 0 is what? 0. 1 plus 1 is 2. And I'll just write down a 2. Wait, we will show you. 1 plus 1 is 2, and then 1 plus 1 plus 1 would be 3. So, so we'd have to carry. So we'll look at that. So let me bring this up just to show y'all this. And multiplication's easy too. So this is addition. So I'd start off, I'd say 1 plus 1 is 2. So I'd write down a 0 and carry. So I write down the 2. Then I'd say 1 plus 1 is 2. So I'd write down a 0. So I'm just writing down a 2, right? You understand that? But I'm carrying the 1. Then I'd say 1 plus 1 is 3. So I'd say 1, 1, that's 3 in binary. Then I'd say 1 plus 1, this would be 0 with carry 1, this would be 1, this would be 1, this is 0, carry 1, and I've added those numbers together.
That's where I was confused with the subtraction part.
The subtraction, we borrow, so on base 10, you borrow a 10. Most people say they borrow 1. Yeah, so you say, okay, I'm going to say 963, and then I'm going to subtract, 84. Well, you say, I'm going to come over here and you write that little 1 up there, but you're not borrowing a 1, you're borrowing a 10. This is not 16, this is 16 now. So what you do is you borrow the base.
So when they said 1 minus 1 is...
No, come on, let me show you. So 1 minus 1 would be what? 0.
No, there, 0, but...
What's this? 1 minus 0? 1. Okay, what would this be? 0. What would this be? 0, 0, 0. Oh my goodness. I need to borrow the base. What is binary? Base 2. I mark this out, put a 2 up there, and that would be the answer.
The book says 1 up there, that's where I got confused.
No, you're borrowing a 2. You borrow the base. So that's what you're borrowing, and you're looking at base 10. So when you borrow the previous number, you're borrowing a 10. Well, actually here we're borrowing 160, but because we're coming from that direction. So when you do base 10, you borrow the base. Anytime you do subtraction, you borrow the base. Now base 16 would be hard, but in base 16 you would borrow what? A 16. And we can look at this. So let's convert this over and see if my answer is right. So we would come up here. And so let's do that. 1, 2, 4, 8, 16, 32, 64, 128. 1, 2, 4, 8, 16, 32, 64. So we'd add what? 128 plus 32 plus 16 plus 4. In fact, to save time, I'm just going to bring up the calculator. And we'll let the calculator do it to check it to see if this is right. So I'm going to come up here and I'm going to go to my programmer's calculator. And then I'm going to go to binary. And I'm going to go 1, 0, 1, 1, 0, 1, 1, 1. Then I'm going to say minus 1, 1, 1, 0, 1, 0, 1, 1, 0, 1. Hit equal. Oh my goodness, that's the same thing.
Now you got to convert it.
We could, we can convert it. Of course, this would have been easier to do in hexadecimal, just to write it down up here. So even up here, notice we had a problem keeping those 1s and 0s in line.
For some reason, the book doesn't put 2.
Well, what the book does is they write down a binary 2. So they write down that. They should write down that up there. which is a binary too, but to me, that's harder than just barring a what?
Right.
Barring a 2.
Right.
That's what you're doing, but and then you got to figure out how to do this subtraction. So if you just write a 2 up there, then it's easy to do that, you know. So that's a really good question. But see what the book did. The book actually writes down a 1 0 up there, which what do we see in our mind? Yeah, we said 10, right? So, but even writing this down up here, guys, even though I'm doing binary math, it would have been easier for me to come up here and just write this down and split it into groups of 4s, starting with the least significant bit, 1, 2, 3, 4, and then I would have said a B7, and then down here I'd say a 7, 5, and then if I'd have drew that line right there, I wouldn't even thought about how to write that down in binary, because once you learn those 16 codes, then you can go between binary and hex and binary, and it's just second nature. So if you're going to do it, but what it does, it gives us the ability to represent real large binary numbers with very few digits. And it's very little chance of making a mistake on that, right? So if I was to come up here and if you knew the patterns, and if I was to come up here and write down this number right here, and I said, okay, y'all write down 1 0 1 0 1 1 0 1 1 1 1 0 1 0 1 1 0 1. Everybody go, huh? All right. But if I was to come up here and take that same number and split it into groups of 4s, 1 2 3 4 1 2 3 4 1 2 3 4, and I called out 2 B 7 A D, everybody would have wrote it down right. And then you could have what? Then you could have converted it to binary. So this is what we use these other bases like base 8 and base 16. The computer has no idea what base 8 is. The computer has no idea what base 16 on the internals. But it can look at a pattern, and so if you tell it, like if you enter your number with an O, then the application knows that those are octal numbers, and then the application will know how to convert those codes over to the actual binary number that it represents. So everything is done. If it's not math, then it's codes. If it's not numbers, then it's codes. And dividing. So I would say, will this go into that? Huh? Will 1 1 0 go into 1? No. Will 1 1 0 go into 1? Okay. Will 1 1 0 go into 1 1 0? How many times? 1. Right? Then I would do what? So this is real easy. So then what would I do? Then I would subtract this. That'd be a 0, 0, 0. Then I'd bring down a 0. Then how many times will this go into that? 0 times, right? And then 0, and that would be my answer. So here you got to learn how to subtract. Multiplication. Huh? 1 times 1 is what? 1. 1 times 1 is what? 1 times 1. I'm doing the top one. So all you do is if you got a 1, you just copy down the top number. If you got a 0, you can write the zeros down if you want to, but you shift. Usually I just shift twice. Then I'd come down here and write the top number down again. Then I'd shift over and write the zeros again. Then I would come up here and write the top number down again. I think I might have lied. Thank you. I figured say I think I made a mistake. So we shift it right here. In fact, what we usually do is just skip one, yeah. But and then I would come down here and write down the bottom, the top number again. Then I'd add them. 1, 1, 2, that's 0 with a carry 1. 1, 2, that's 0 with a carry 1. 1, 2, 3, 4, that's 0 with a carry of 2 ones. 2, 3, that's 0 carry 1. That would be 1 with a carry 1, 1, 1. So I just count the number of ones, and I know I get a carry for every pair. So we came down through here, we counted 1, 2, 3, 4 ones. So that's 0 with a carry of 2 pairs. And so once you learn those little tricks, this is so much easier to me than decimal math, because you're just adding ones, right? Ones or zeros. So this is the way we multiply. So we multiplied this in decimal. We'd see I come up and get, huh? 1, 1. So this is 1, 2, 3, 4. So that's 0 with a carry of 2 pairs.
If we have like 11 ones.
Oh yeah. If you have 11 1, that would be 5 with and an odd. So if it comes up at a odd, you'll always end with a 1 in the bottom, right? Y'all understand what he said? And this, y'all don't have to do this, and this is why. But this is what I'm saying. This is neat stuff, you know. And you could do math in any base, but when you get into like base 16 and you're trying to, you know, figure out what the number is, it's real hard. But binary math is fairly easy if you understand the concept. If you understand decimal math totally, then binary math is a lot easier, but it's a lot more cumbersome because you're dealing with more digits to represent the same number. So this is why binary is so efficient inside computers, because you got to have circuits that do the math. So every function inside the arithmetic logic unit, it's got a digital circuit in there that does this type of math that you specify. And now we're only dealing with very, 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 very ones and zeros. So it means the circuit that does the math is very, very simple. So even when you enter an 8 on your calculator sees that as a code and basically does the math in what? Ones and zeros. Very impressive. But y'all need to know how to do that now. In fact, there's not even any in your worksheets or any of your labs. And really, there's really no need to do it inside a PLC, because the PLC will do the math for you. So later on, you know, it's a computer. So what we can't do in relay logic, and this is what's nice about the other classrooms, we got those relay panels up there that actually do the logic, and we have some circuits wired up there so you can see the big difference between doing it with a PLC. But so on this one, we're going to get through counters and timers. But you know, if you take PLC 2, we do math, and computers love math. You know, they'll do it. And all you do is you don't do the math, you just tell it to add, right? You tell it to subtract, you tell it to multiply, you tell it to divide. Some computers do trig, so it's all in part of the instruction set. So every PLC supports a certain amount of instruction, by the way, in the computers. If y'all read that section of the book, this is how we tell our computer what we want it to do. So every microprocessor, I'm see if I can find my instruction book for the i7 processor. it's about that thick. But so every PLC has what we call an instruction set, and the RS Logic 500 is very extensive. So one of the things that when you specify what PLC you got, it loads in the instruction set for that PLC. So that means if it don't support trig, then if you look at the trig section, it'll be grayed out. Which all that means is that PLC doesn't do what? Doesn't support the trig functions. So a lot of PLCs don't do that. So that's another important thing, is you need to make sure the PLC that you pick has the instruction set that you need. So if you need to do high level math like trigs and stuff like that, this one has an instruction where you can actually enter the equation. You actually enter the equation. And so you can do really complex math with this guy. So it's got an equation editor, which is pretty cool. And we'll look at that if you take the second. We looked at words. We looked at bits, nibbles, bytes, words, double words. Most of your PLC. Wait. Yeah. So most of your PLCs don't call them double words. This is what these computers right here call them, double words. PLCs refer to them as long words, and your computer calls them quad words. PLC calls these double lawnmowers. And this is about as far as we go, guys, in PLC, because there's really no need to represent, trillions inside of PLC. So this, and you can tell how many numbers you have how many digits you have available in any numbering system by just taking the number of digits and then just raising, I don't want that one, just raising it up to that power. So these are base 2, and this would be 64 bits. So a double long word would be 64 bits. So right here, here's my X to the Y. These are all base 2 numbers. And then I would raise this up to the 64th power. And that's how many numerical combinations. Actually, the biggest number we could represent would end with a 5, because this is counting 0, and 0 has no weight. So I can't even say that number. I don't even know what it is, even if I split it into groups of 3s. So there's really no need to have the ability to go to any higher resolution than what we've got, because this is a number that's basically unimaginable to us. Even the debt of the United States would be less than this. So yeah, with what's going on, and I don't know what they're going to do, guys. They're not collecting all that tax they usually get from all these companies. It's going to be interesting. So it might get there. Cortex, like I said, these are your 16 characters. This would be represented in binary. This would be what it equals to in depth. So if I was going to count in hex, and we did this in the other class, and this gets people confused too. You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you go A, B, C, D, E, F. What if I wanted to keep counting? I'd put a 1 up there, just like you do, and I'd put a circle right there. But that's not 10. That's actually 16. So this combination of 1 and 0 is the base in any numbering system. So 1 0 in base 8 would be equal to 8. 1 0 in base 10 is equal to 10. 1 0 in base 2 is equal to 2. And then I would start all over. 1 1 1 2 1 2 Rich. 1 3 1 4 1 5 1 6 1 7 1 8 1 8. No, I'm sorry. 1 9 1 A 1 B 1 C 1 D 1 E 1 F 2 0. Counted to 16 twice, and we just keep going. So when you run out of combination, you just add another digit and you keep going. And we can represent the number of numerical combinations, including 0. We can take the base, so base 16, base 2, and we have 4 digits. 2 to the 4th is equal to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I ran out of combinations. So you can calculate, but that's including 0. So you can calculate the number of numerical combinations that you can represent in any base just by taking the base and raising it to the y. And of course, 1 digit of base 16, that'd be 16 raised to the 1st. That's equal to 16. Well, notice those two match exactly. So that's the trick. So that means I can use 4 bits of binary to represent each digit of hexadecimal, because they have exactly the same number of combinations. It's the compressor. This is the compressor. That's the compressor for the whole building. How did we end up with it? Well, this used to be all automotives down here. They had lifts out here. In fact, you can see down in 121, they still got one of the lifts in there. Of course, they took them back out, but this used to be all automotives. So that's the big compressor. What we do is that both of our lines here use the compressed air. All the robots over next door use compressed air. So originally, when we bought them, each one of them had their own compressor, and they would all run at different times. So technically, the compressors run all the time, but that's a huge one. So Hex, anybody got any questions on that? So it would be so much easier for me to give out 387A. For me to give out 110111110. Say, could you repeat that? Could you repeat that? Could you repeat that? Because even when we write it on the board, because odds are you can only see a certain number of bits at a time, and you're constantly doing this, right? You understand? And what happens sooner or later, your ones and your zeros start running together, and you forget where you was at, and you end up with the wrong number. But if I was to write, even though I want you to do binary, if I gave it to you in hexadecimal, it would be very, very simple just to come up here and take that and write down the code, write down the actual binary number that hexadecimal equals to. And you can see I've been dealing with it a long time, so but I know it takes a little learning curve. But if you're going to deal with computers, you're going to have to deal with this. I mean, unfortunately, in fact, for the IP address, the IP, we called it IPv4, which is version 4 of IP addressing. This is a 32-bit binary number. Well, the problem is they understood that people couldn't understand binary. So what they did is they came up and split it up into bytes. So that'd be 4 groups of bytes. And then they took each byte and converted that to a decimal number that we usually call a dotted quad. You'll see this. So this is command prompt, and if you're going to deal with networking, you'll be very familiar with this. We have a command called ipconfig, which basically is going to show me the IP addresses of my computer. Oops. Forgot the D. And so this shows me the IP addresses. So right now we have IP addresses for just about anything. So Bluetooth uses your IP addresses. So this is the IP address right here. So 10.99.10.6. Some people call that a dotted quad, but it's in decimal. And so if I wanted to know the actual IP address, then I would have to take each one of those dots and write down convert it using decimal to binary and convert those. Well, we thought that would be enough IP addresses to last forever, 2 to the 32nd. We said that was enough to ask for. But think about the number of IP addresses you have in your house. Your phone, every phone you have that you connect to Wi-Fi has an IP address. If you use voice over IP, which is a lot of people's using that instead of having wired telephones, you're using IP addresses. Every Bluetooth device has an IP address. So they thought 2 to the 32nd would be enough to last forever, but it wasn't. So they came out with a new version they call IPv6, which is a 64-bit binary number. Well, what they decided to do is not do it in decimal. They decided to do it in hexadecimal. So here's the IPv6 for you, FE80, and then this is a repeat. 60D5 9F2H. So I could take that. It would be a lot easier for me to convert this to the binary than it would be going from decimal to binary. So IPv6 is actually displayed on your computer in hexadecimal. But IPv4, which is local, now the internet, about 95% of the actual internet has gone to IPv6. Local networks, which is what we're on, 10.9.10, that's a private network IP. So what that means is that they're still using IPv4. So all your PLCs will use IPv4, internet version, IP protocol 4, IP4. So that's another thing right there. This is the subnet mask. So they're giving it to you in decimal, but the subnet mask is 1111111111. 1111, 1111, 0000, 0000. So I can convert those real easy because it's 255. But that's the subnet mask. The way IPs are set up is there's two portions of an IP. The most significant bit moving toward the least significant bit, we call that the network ID. And then the least significant bit moving toward the most significant bit, we call that the node ID, or the actual computer. The subnet mask shows your routers what is what. So this says the first 16 bits is the network ID. So basically with this subnet mask, I could have 65,536 networks. And then I could have 65,536 computers on that network. So that's what that subnet mask is. So if you don't know how to go to binary, so this is easy because this is 255, but if you don't know how to go from decimal to binary, you couldn't even figure out a subnet mask on a network. So we had classes. We had classes A, B, and C. Well, class A was 255.0.0.0. A class B was 255.255.0.0. And then a class C was 255.255.255.0. But they realized that wasted a lot of IP addresses. So now we have what we call classless IPs, which means you can split them anywhere you want to. So I could have a 255.198.2 on my network and use whatever subnet mask I wanted to. So that means if 255, so the old ways 255, those are all 111.1.1.1.1. So they were real easy to figure out. But with classless IPs, which we use now because they don't waste any IPs, subnet masks can break anywhere. So if you don't understand that, y'all probably seen this before and didn't understand what was going on. Like a gateway is what converts it over to a different protocol. So when you go out your router, it's got to have a gateway to actually go to your modem. So that converts protocols and then switches and all that. So this is why even if you want to get into setting up these IPs on these guys, you got to know this stuff. You got to know how to set up a subnet mask. You got to know what to do and how to assign those IPs. So these guys don't come with IPs built. IPs, by the way, are logical. They're not physical. They're logical. So that means I can have the same IP inside this local network that another company has inside a local network because these networks. But on the internet, you can't duplicate IPs on the internet because everybody's got to have them. Got to have them. So subnet masks and that kind of stuff is pretty interesting. So even if you don't get that far, so this is counting in hexadecimal. Of course, I didn't go this far. This goes all the way up to FF, which is 255. Yes, it's counting in hex. And the sided in red is counting in decimal. So I did this chart by the way, quick for a lot. And then if I hit FF, what would I do? I'd go to 1 FF. I go to 1000 and keep going. Octal, we looked at that. We split the binary numbers in the groups of 8. So I could have this number right here, 635, and that could actually be a decimal number. That is legal. This number is legal in octal, and this number is legal in hexadecimal. But each one of them would have a different weight. So one of them uses powers of 10s, one of them uses powers of 8s, and one of them uses powers of 16s. So this is why most of the time I'm going to try to do this, is I'm going to specify the base down here at the little bottom. That'd be base 8. So this would be 8 to the 0, this would be 8 to the first, and 8 to the second. If this is base 10, this would be 10 to the 0, 10 to the first, 10 squared. If this is base 16, then each one of these, this would hold a weight of 16 to the 0, 16 to the first, 16 to the second. So this would be the biggest decimal number. This would be, and this one would be the smallest. This would be legal. That number right there would be legal in 4 different bases. So it would be, those digits or those symbols would be legal in 4 different bases. So we need to make sure that we let you know. It's either going to be stated, it's going to say convert, like in your text, it says in your lab, it says convert the following binary numbers over to. So I don't know if, I can't remember if they put the little subscripts in there or not, but they specify exactly what you're doing in that lab that you're doing. Okay, guys, we need to take a break. We'd like to take a break every, by the way, on this one, the water fountains are locked down. So I think I sent that out that if you need to drink something, you need to bring it out. The restrooms are in this building is out the door to the right. The men's door is usually latched open. There's, of course, hand soap in there. And of course, these faucets have a flat thing, so you can hit them with the back of your hand. If you don't want to do that, just before you start washing your hand, go ahead and get your paper towels first, and then wash your hands, and then turn it off with your paper towel, if that's what you feel comfortable. And by the way, before we leave here, we're going to have to sanitize the room. We got all the stuff in here to sanitize the desk, so we'll do that before we leave. So, restrooms out the door to the right, first hall to the right. And I think the men's should be blocked open, so you shouldn't have to open that door. Even if you're not going to take a break, you need to.
How many minutes?
10 minutes. Need to stand up, walk around. If you go outside, you need to have your mask on while you're in the room. If you go outside, you can take your mask off, but you need to make sure you social distance when you go out there.
I was working and pick up stuff up. Try not to disturb you.
And digital, if that's one of their classes you need to take. Octal numbering systems, that's counting in octal codes. System of words, letters, figures, and other symbols substituted for other words, letters, and figures. The codes that we run into in PLC is binary coded decimal, gray code, American Standard Code for Information Interchange. EFTDAC, the book is totally wrong about EFTDAC. EFTDAC was the code that was originally used by IBM mainframes. This has long been obsolete. It's actually what's called extended ASCII, which I didn't give that code out to you. And of course, Unicode. This is only supported if your PLC supports a web browser, which the 1100 does, by the way. The 1000 doesn't, so you can actually access it through the web. You can't program it through the web, but you can send information to a regular computer through just a regular web page, which is pretty. The 1000 doesn't support web pages. Binary coded decimal, each 4 bits of the binary number are grouped to form a decimal number. 4-bit groups representing 10, 11, 12, 13, 14, and 15 are not valid. Numbers in the BCD number system. Only 4-bit patterns representing 0 to 9 are valid, and here they are. So with 4 bits of binary, I can represent 16 combinations. BCD sacrifices 6 of those combinations. This is not a number system, it is a code that we can directly represent decimal numbers. It doesn't go 1, 2, 4, 8, 16, 32, 64, 128. It goes 1, 2, 3, 4, 8. Some people call it the 1, 2, 4, 8, 1, 2, 4, 8 code. So technically, but the problem we have is when people see this code, they think they can go from decimal to binary and call it the answer. BCD is not a number system. It is a code that we use to directly represent decimal digits. So these are the only codes we have. That would be invalid. There's no such thing as that code in BCD. So here's the codes on the left, which represents the decimal digit. We can go directly from this by memorizing these codes, and it's 1, 2, 4, 8. So 1, 2, 4, 4, 8. This is not a numbering system, it's a code. So if I wanted to represent 963, I would write down the code for a 9. I'd write down the code for a 6. I'd write down the code for a 3. And this is BCD. This is binary. It does not go 1, 2, 4, 8, 16, 32, 64, 120. It goes 1, 2, it goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. This is not a number system. This is a code.
Which one they go? 1, 2, 4, 8,
That's binary.
binary, they go-
Yeah. So binary, if I wrote this down, I would come up here and the same, if this was a binary number, this is binary, base 2. This would go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. I would add, to get the weight of this number, this is a number system, it is weighted. Then I would add 2048 plus 256 plus 64 plus 32 plus 3.
Plus 3, plus 2,
3 and 1 is 3. Okay. So whatever that answer, we're not doing, this would be the decimal system.
so it'd be like 9, 6,
We're not worried about that. Up here, I would say, this is BCD. It represents 9, 6, 3 base 10. This is not a numbering system. It does not go 1, 2, 4, 8, 16. What we do is we use 4 bits to represent each decimal number. It is not weighted. It does not go 1, 2, 4, 8, 16, 32. It goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. It is not weighted. It is a code.
The binary starts with 1 or 0?
Binary starts, every numbering system starts off with 1.
The next one is 4, 0.
Well, this right here is 2 to the 0 power. You can take 5 million and raise it to the 0 power and it would be 1. So in any numbering system, in fact, base 10, we call it units, right? Which means that first digit is in ones, right? You know, it's not in zeros, it's in what? Ones. So every base, if I was to write down 5, 6, 3, base 8, this holds a weight of 8 to the 0. Well, what's 8 to the 0? That's 1.
Well, that's like,
This would be 64, right? You understand? This would be 256. But, because that'd be, I'm sorry, this would be 8. And this right here would be 64. So every number system, that least significant bit is always multiplied by what? By 1. Whether it was a base 16. So if this is base 16 and it said FB3C, this is 16 to the 0, so that's 1, right? And then the next one would be 16 to the first, which would be 16. This would be 16 squared, which is 256, and this would be 16 to the third. I have to look that one up, even though I should know that. 1024. But BCD is the way we can easily represent decimal numbers as a code. In fact, BCD has been around so long that there's a technique that you could actually add BCD. So most of your PLCs will support addition of BCD codes. In fact, if you take digital, we have BCD adders, we have BCD counters, because it's a very standard code. And it's good for us because it directly represents the decimal number system. And what number system have we learned all our life? Decimal, yeah. But it is not weighted, it's a code that we can directly represent decimal numbers by representing each decimal digit with 4 binary bits. But you're sacrificing all these combinations, but it's very easy for us to understand.
Like on here, it goes not.
Well, if I wanted to do 15, this would be decimal. If this was 15 decimal, then I would have, this would be the code for a 1. And you have to use 4 bits because it's the code. You can't drop off leading zeros. And then this right here would be the code for 5. This is BCD. So it don't go up to 15. We sacrifice, of the 16 combinations, we sacrifice 6 combinations, right, to do what? To be able to do this code. Now, the problem is somebody in this class is, when I say convert the following binary numbers into decimal or vice versa, or I'm sorry, convert the following decimal numbers into binary, you're going to write down the BCD code and you're going to be wrong. And I wish y'all could make a liar out of me.
So repeat that one more time. Convert the letter.
Somewhere in this class it's going to say convert the following binary, the following decimal number into binary. It's somebody in this class, so it might be like, where's my writing it? And like I said, y'all make a liar out of me. So I'm gonna say like convert 100. I'm gonna say convert 100 base 10 into binary. Somebody in this class is gonna go 001 0 0 0 0 0 0 0 0. It's not, it's BCD. Now in decimal, that's actually what? 1, 2, 4, 8, 16, 32, 64, 128, 256. So that's actually equal to 512. It's not equal to 100. Instead of going through, okay, I'll take 100 and I'll set up a binary code, 1, 2, 4, 8, 16, 32, 64, 128. And then I'll start subtracting and convert it into binary, which is the way we learned how to do it, right? By repetitive subtraction. This is not, it's a code. But somebody in this class is going to think it's so easy to go from decimal to binary, but what they're doing is they're going from decimal to binary coded decimal. It's a code. A code is when we use something to represent something else. It's not the same, right? You understand? It's just like the ASCII code for the letter A is 41 for a lowercase a. And that's hex, by the way. It's not the letter A, it's the code that represents the letter A, right? Y'all understand that? If I converted that to decimal, it would be a totally different number. So what we have to understand is we have to have codes. And BCD is a very simple code, right? You understand? It's very simple. Now you got 10 patterns. In fact, you only have to represent the patterns. You know, you can go what? 1, 2, 4, 8. And then just look at that. Well, I want a 10. Well, what's a 10? So 1, 0, 1, 0, that's a 10. That's even in binary, but it's not representing the next digit up there, right? You understand that? So there's no such thing as an F in binary. There's no such thing. This right here, I mean in BCD, that 4-bit code is invalid.
The answer to the question about 100 is
60,
1, 0, 0, 1, 0, 0.
right, 64, basic hex. That would be what? That would be decimal to binary. Right. That's exactly right.
Okay.
But what somebody in this class is going to do? They're going to convert the code because it's so easy. They don't have to do any math. They just do 1, 4, 2, 4, 8. They just write it down. So y'all make a liar out of me. Be the first class I've ever taught. Somebody don't do that on a test. We looked at this. Number of binary combinations is the base raised to the number of digits. The biggest number you can represent is each number of base to the n minus 1. Because the number of combinations includes 0. So if I say how many numerical combinations can I represent with 1 digit of base 10? So that'd be 10 raised to the first, which comes out and gives me 10 combinations. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how many numerical combinations we can represent with each digit. What's the biggest number I can represent? 9. So that would be this little formula. That's the biggest number you can represent. So 16 bits of binary. Look it on your chart. Look at 2 raised to the 16th power. What would that be? That would give me what? 65,536 combinations. The biggest number I could represent would be 65,535 because that includes 0. 0. 0 is one of your combinations, but 0 has no weight, right? You understand? So this gives you the number of numbers you can represent, and that's including what? Including 0. So this will be coming pretty important back in not in this class. In digital, it's very important. BCD is not a numbering system. It is a code to convert the numbers from any other numbering system besides decimal to BCD. The number must be first converted to decimal. So if I had the binary number like this, let's do that one while ago. And I wanted to convert that, if I wanted you to convert that to decimal, you would not come up and write 65. Because what you just did is use BCD. What you have to do is you have to go what? 1, 2, 4, 8, 16, 32, 64. Of course, we don't have 64 and add them together. Just like we taught. Then you can take the decimal number and convert it directly to BCD. So you cannot go from binary to BCD. You cannot go from octal to BCD. You cannot go from hexadecimal to BCD. The only thing you can go to BCD is from decimal, because it's representing decimal numbers. Then represent each decimal digit with a 4-bit BCD code. Now, notice how many times I put BCD in red. BCD is not a numbering system. So each digit does not hold the weight to the base all the way up the line. It goes 1, 2, 4, 8, 1, 2, 4, 8. You don't go 1, 2, 4, 8, 16, 32. Right? You understand that? It's a code. And like I said, it's been around so long, just about all microprocessors that I know to has a BCD add instruction. They can subtract and add BCD. In fact, if you do take digital, we have BCD counters because they've been around so long. Gray code. Gray code is a code that we use. The problem we have is we deal with speed control or counting and these bottles and stuff are flying past these counters that they look to us like they're blur. And we've got to have a counter that keeps up with that. One advantage of hardware over software is hardware is faster, the physical point. So a digital counting circuit would always be faster than a group of code that represent a counter. So it takes quite a bit of actually machine language to represent or cause a PLC to count. So PLC counters are relatively slow, and they can't keep up with these encoders that we use to represent speed and position on some of these robots. There is no way in the world a PLC counter, a software counter can keep up with a hardware counter. So what happens is that one thing, and also we have what we call a propagation delay. So if I was to come up here and start counting like this, well, this is binary. As I start counting, starting in decimal. So this would be 0. This would be a 1. This is 0. This would be a 1. This would be a 2. Well, when I went from a 0 to a 1, I went from a 1 to a 2. We had 2 bits that had to change. So this one had to change to a 0, and this one had to change to a 1. Well, I went from 3 on a 3 to a binary 3. I only had 1 digit that had to change. When I went from a 4 to a binary 4, this had to change, this had to change, this had to change. I went from a 4 to a 5, this one changed and this one changed. So here we had 1, here we had 2, here we had 3, here we had 2, here we have 1. So what happens in search tree of programs, we have what we call propagation delay, and this is how long it takes to propagate through the whole number. And the more bits you add, the longer it takes for when, at least in the NIFA bit updates, the longer it takes to get out to that most significant bit. And the more bits you have, the more propagation delay you have, the more you have that change, excuse me. So what they wanted to do is they wanted to come up with a counter where instead of using the binary code, it used a code called gray code. And if we look at counting in gray code, so this is counting in gray code. This is not weighted, this is a code. But this would be this would represent a count of decimal 1, this would be 2, this would be 3, this would be 4, 5, 6, 7, 8. They are not weighted anymore. But when I go from a count to a 0 to a 1, we had 1 bit change. When I went from a 2 to a 3, we had 1 bit change. When I went from a 3 to a 4, we had 1 bit change. When I went to a 4 to a 5, we had 1 bit change. When I went to a 5 to a 6, we had 1 bit change. When I went from a 6 to a 5, we had 1 bit change. When I went from a 5 to a 4, we had 1 bit change. So this is not a number system, this is a code. But what happens is for each count, no matter where I go from one count to the other, where am I counting up or counting down, I only always have how many bits that change? 1. So a gray code counter has the ability to count extremely fast because the propagation delay, how long it takes to propagate through the number, is a lot faster. But it is not a number system, it is a code. So right here, this would be a count of 8. But if you went over 1, 2, 4, 8, it would only be a 4. But it's not a number system, it's a what? It's a code. To convert it, you have to learn about an exclusive OR operation. So basically, come up and write down a binary number that we want a count that we want to convert over. And then we drop this bit down. Then we take this one, and then we exclusive OR it with this guy. So that's going to be a 0, 1, so that would give us a 1 right here. Then we'll take this one and exclusive OR with that one, we would get a 1. Then we take this one and exclusive OR with that one. I should have done it, 0. Let's see. This is a 0, sorry. So this is a 0, with exclusive OR that would get a 1, and so that would be the code. It has nothing to do with the weight. And then when we come back, we would go back the other way. So this is done with a computer and a heartbeat. And it don't do every count, it just does the end count, right? You understand that? So gray code counters are extremely fast, and like I said, this is fun. I know how it does it, but do we need to know this in this class? No. And what did I tell you to do it on your worksheet? To do what? Skip it. But it's a code, and that's what we have to understand. It's a high speed what? Counting code. How many bits change per count? 1. Whether they're counting what? Whether they're counting up or down. So that's all you need to know about gray code. This code you probably need to know. You'll look this up in the chart. Alphanumeric code gives us the ability to represent letters, decimal numbers, and some symbols. The first code we'll look at is American Standard Code for Information Interchange, or ASCII. This is a 7-bit code. So that means we can represent 2 to the 7th combinations. So that's going to give us 127 different characters that we could originally represent with the ASCII code. Well, it's actually 128 because 0 is the code, sorry. 128 different characters can be represented. That is often seen in byte groups or bits of 8. The 8th bit is the 8th bit in a 1 byte of transmission data is used for something called parity. The ASCII chart is most often given in hexadecimal, because hopefully we can think about going through that. So this is the ASCII code chart. It should be on the back of your sheet. So the first 2 columns, these are what we call control codes, where we can actually control devices. uh, null, start of transmission, intercept transmission, not acknowledge, acknowledge, ring the bell, end of transmission, horizontal tab, vertical tab, line feed. So these are all what we call control codes that would tell your printer or whatever to do different things. 20, so the actual code for a space is, this is hex, the most significant digit. So we read the columns first, and these are the least significant digits. We read the rows second. So the ASCII code for a space would be 0, 0, 1, 0, 0, 0, 0, 0. This would be ASCII.
Right.
This is in hex because it takes less digits, right? So if we did it the other way, you would have to convert it over anyway. So some of them you see it in binary. So what I did is I looked at read the most significant bit, the column first. So it's in column 2, and it's in row 0. It should be 20 base 16, 20 base 16. Then I took that and I converted it over to the actual code. And I can't go over and spell ASCII. So if I was going to spell my name, I would come over here and I would find R. So here's R. So it's in column 5, row 2. So that would be 52 base 16. So it's going to be 50. Since it's base 16, I can convert it over, right? 62. This would be ASCII. I'm just going to put an A out there. And then I would use the lowercase I. So lowercase I is 69. 69 base 16. So it'd be 69. And this will be ASCII. C. Column 6, row 3. Then H would be column 6, row 8. $63 ASCII. 68 8 rich ASCII. So that's my name. So if I wanted this guy here to display rich up there, I would have to send these codes to it. This is still a standard code. In fact, the Unicode, the first 250, the first 127 characters are actually the OASCII code. So you'll see they'll all end up like this. So an A is 41. So if I looked up, if I was going to come over here and insert a symbol, can I do that here? So insert a symbol for the letter A, uppercase A. Go back up. Uppercase A, 00041. So the OASCII chart is still in Unicode, so they kept that to make old websites that were written using the OASCII code in English still valid. So we could, but this is in hexadecimal, 41. If you look at the chart, ASCII for uppercase A is 41. And then they came out with what they call and this is these are the control codes. Then they came out with what they call extended ASCII, which is this guy. So this is what the book is called in EBCDIC, by the way. And EBCDIC is not extended ASCII. It's a code. You can look up the EBCDIC chart. It's still out there on the internet. It's not the same. So the guy got this wrong. And I understand, guys. I've written books, and I understand mistakes. So, So notice with extended ASCII, we can do a lot of special characters. Do a lot of groups. But it's still not Unicode. So this is an ASCII code. These codes are not the same as Unicode. You'll have to look them up. Some of them are. I know Micro is the same. Yeah. So these are extended codes. Oh, by the way, if you enter them in on your numeric keypad, you have to enter them in decimal. You can't enter them in binary. So what you do is just hit the Alt key on your keypad, on your computer, and on your numeric input. Just enter these codes right here, and these codes will pop up, so you can directly enter ASCII into your keyboard. Unicode, I can't remember, something D, you gotta enter a couple of keys to enter the Unicodes directly in from your keyboard. So this is Unicode, and EFZADEC, this is actually EFZADEC, but it's still a code. This was originally what IBM used on their main branch in the IBM computers, but they eventually adopted over to ASCII. So everybody just about went to ASCII after a while. Of course, now they're using Unicode, but this is not what the book teaches. The book teaches the enhanced ASCII or extended ASCII. That's not true. This is actually ASCII. So we do the same way. We'd read the columns, right? And we'd read the rows. Okay. So here in uppercase A would be a C1. Where over in the ASCII code is a 41 hex. So the guy did this wrong. I actually looked this up on the internet because I knew it wasn't right. When I saw his code chart, I knew that was extended ASCII, not EFZADEC. Extended binary code for I forgot. It's an acronym there. Unicode, we basically use the Unicode form 16, which gives us 65. It actually goes up to 32. This is not usually used by the internet. The internet reads off in Unicode 16. Unicode 8, that's just your ASCII code, guys. That's your ASCII code. 16, this is the one that Microsoft Word uses. This is the one that the internet uses, which gives us 65,536 different characters. And like I said, I'm not going to write those up here. This is 8. And then, of course, if you wanted to see what the code was, and you can search and say, Unicode. You can search up for Unicode or how to enter Unicode from your keyboard, and it'll tell you that. So you usually enter that, I think, in hexadecimal if I remember right. But you hit a sequence of keys and you can enter those codes and it'll pop up. Usually it's a lot easier just to type it in or select it out of a chart. So Unicode, like I said, if your PLC supports the web servers, then you might have to learn that. But now hopefully a lot of this makes a little more sense than what you thought you knew, right? So any questions? Are y'all all lost? Head smoking? Head smoking? But there's a lot, and this is the problem we have with PLCs. You've been dealing with these guys for so long. They do all the work for you. I mean, they do everything for you. So you use the decimal number system. So I come up here and bring that calculator up. I enter digits, but I don't actually know what's going on. This computer has no idea what the letter A is. All it knows is it's got a code that tells it to turn on a certain number of dots to display an A up on the screen. So these are nothing but dots. I might go and find my microscope and let you actually look at the screen and see the 4 different colors. So we actually use 4 different colors. Black, we have a black background. Then we have green, blue, and red. And they're all just dots, little dots that they turn on and turn off. But they're so small that our eyes do what? Just blend them together. That's what they do. And sometimes on these big old Megatron, these big screens, when you get up close, you can actually start seeing the what? You can actually start seeing the dots, the three colors, the 4 colors, because they're on a black background. So your TV does that. Everything on your TV is in dots. And then pixels. Pixel is a group of dots. Is what it is. That's all the same color. When you set up your resolution, that's what you're doing. You're setting up the size of the pixels, and you'll never be able to have a resolution that's smaller than the dots, space and dots on your. So that's why on one computer you might have a big resolutions that you deal with. And the problem we have is people want to use these big resolutions that their eyes just can't do what? They can't see. So. And they want to use 32-bit color, and you can't discern 32 to 32nd, and you're eating up a bunch of memory. But if your computer don't support it, then George's computer does 32-bit color. Yours only does 16-bit color. And you think he's got a better computer than you, but you throw the same image up on your screen, and they look exactly the same, even though George is going to say his looks better. Yeah, anything over 16-bit color, guys, is usually a waste of time. That's 65,536 different colors. Our eyes just can't discern that many, especially when you get my age. So any questions on this? Anything I want to go back and look at before the test? So the book is wrong on gray code. It doesn't do it. It does it in nibbles, but it's not. It's the whole number, no matter how big it is. That's the gray code for the numbers. Your computer has no idea what a nibble is. All it understands is that number. So if it's a 64-bit number, it's a 64-bit number. It's not divided into nibbles and stuff like that. It's up to the application to decide. This guy right here uses words.